Rates and unit conversions are an important concept to master before taking the SAT. I recommend solving most rates problems by treating them as unit conversion problems using conversion ratios. For instance, how many miles are in 750 feet? The process is simple. Start with a value and multiply by a conversion ratio. For instance, if we were asked to convert 750 feet into miles, the starting value is 750 feet. The conversion ratio would be a fraction that expresses the fact that there are 5,280 feet in 1 mile. You can arrange that conversion ratio into a fraction, and it's up to you to decide which one goes on the top and which one goes on the bottom. For instance, I can use 1 mile over 5,280 feet, or I can use 5,280 feet over 1 mile. The way to decide is to do the opposite of whatever you started with. This will get our original unit to cancel out. We started with 750 feet, which is really a fraction with 750 feet on the top and 1 on the bottom. Since the unit feet is on the top, we should arrange our conversion ratio as a fraction with feet on the bottom. When I multiply by this ratio, I'm not changing the value of what I started with. A fraction with 1 mile on the top and 5,280 feet on the bottom has the same value in its numerator that it has in its denominator, since 1 mile is the same distance as 5,280 feet. So this fraction is equal to the number 1. Since multiplying something by 1 doesn't change its value at all, I can multiply by as many conversion factors as I want to. So, feet cancel with feet, and all we're left with are miles. We're left with 750 times 1 across the top, and 1 times 5,280 on the bottom. 750 divided by 5,280 is 0.14. So, in 750 feet, there are 0.14 miles. Lots of high school students would have approached this problem by cross-multiplying. 5,280 feet over 1 mile equals 750 feet over X miles. This approach is right, but as you see, in a situation where you have to carry out more than one conversion at a time, it would be difficult to solve by cross-multiplying. Now let's take a look at the next problem. It takes 5 complete turns of a crank to raise a fishing rod hook 2 feet. At this rate, how many turns will it take to raise the hook 4.4 feet? You always want to start with the basic value the problem is giving you. In this situation, the value is 4.4 feet. We need to know how many turns of the crank is equivalent to 4.4 feet. Let's take that value and multiply it by the conversion ratio. 4.4 feet is really a fraction because any number is really itself over the invisible number 1. And since we have feet on the top, we need to arrange our conversion ratio with feet on the bottom. Although the ratio of 5 turns of a crank to 2 feet is not a normal conversion, like 1 feet to 12 inches, in this situation, we can treat it just like a regular conversion ratio. This is because, since you get 2 feet for every 5 turns of the crank, the two things have the same value. And if I arrange them into a fraction, I get a fraction that's equal to the number 1. So we'll multiply our starting value by the fraction of 5 turns over 2 feet. We have feet on the top and feet on the bottom, so they cancel. Across the top, we have 4.4 times 5, which equals 22, and the only unit left is turns. Across the bottom, we have 1 times 2, which equals 2. Now we can divide 22 by 2, and the answer is that it takes 11 turns of the crank to raise the hook 4.4 feet. Next problem. Patty uses 2 gallons of paint to cover 875 square feet of surface. At this rate, how many gallons will she need to cover 4,375 square feet of surface? Notice that our starting point is the last thing they gave us in the problem. This adds a tiny bit to the level of difficulty. We start with 4,375 square feet, and we multiply by 2 gallons over 875 square feet, purposely putting square feet on the bottom so they'll cancel. Square feet cancels with square feet, and across the top, we have 4,375 times 2. And across the bottom, we have 1 times 875. So we have 8,750 over 875, and the only unit left is gallons. When we divide that out, we will see that it takes 10 gallons to paint 4,375 square feet of surface. Here's a problem that will involve a double unit conversion. A subway car passes 3 stations every 10 minutes. At this rate, how many stations will it pass in 1 hour? Our starting value is the fact that the car will be traveling for 1 hour. The subway car passes 3 stations in 10 minutes, so we'll multiply that in as our conversion ratio. Since we had time on the top of the first fraction, because any number is really itself over 1, we need to put time on the bottom. Since one of the time units is hours and the other is minutes, we can throw in a second conversion ratio to take care of the difference. There are 60 minutes in 1 hour, and we'll keep the minutes on the top to cancel out the fact that we have minutes on the bottom. Now, hours cancel with hours and minutes cancel with minutes. Across the top, we have 1 times 3 times 60, which is 180, and the only unit left is stations. Across the bottom, we have 1 times 10 times 1. That leaves us with 180 divided by 10, which divides out to 18 stations. Therefore, in 1 hour, the train will pass by 18 stations. Here's another problem that involves more than one unit conversion. If it takes a guitarist 1.5 days to write 2.5 songs, how many hours does it take the guitarist to write 3 songs? Here, the starting value is 3 songs, and any numbers relate itself over 1. The conversion ratio is 1.5 days over 2.5 songs, purposely arranged with songs on the bottom so that they'll cancel. But the problem asks for an answer in hours, so we need to throw in another conversion factor to get the days to turn into hours. There are 24 hours in 1 day, and we're purposely going to put days on the bottom to get the unit days to cancel out. Now, we can go ahead and cancel. Songs on the top, songs on the bottom. Days on the top, days on the bottom. And we can multiply across the numerators, leaving us with 108. And the only unit left is hours. And across the denominator, we have 2.5 times 1. 108 divided by 2.5 is 43.2, so it takes 43.2 hours to write 3 songs. Next problem. The planet Caleb takes 1 complete rotation on its axis every 36 hours. If it turns at a constant rate, through how many degrees does any point on Caleb, except the poles, rotate from 9 a.m. January 14th to 9 p.m. January 17th? If we approach this as a conversion problem, we're looking for a starting value that we can multiply by 1 or more conversion factors. One thing about this problem is that the starting value is not given to us outright. First, we're going from 9 a.m. to 9 p.m. on the 14th, which is 12 hours. And then we're going from 9 p.m. on the 14th to 9 p.m. on the 17th, which is 3 full days, or 24 times 3, which is 72 hours. So altogether, the amount of time we're starting with is 12 hours plus 72 hours, which adds up to 84 hours. Now we have our starting value. We can take that and multiply it by the fact that there's 1 rotation every 36 hours. Then we can throw in the fact that there's 360 degrees in 1 rotation. Hours cancel with hours, and rotations cancel with rotations. Multiplying across the top, we have 84 times 1 times 360, which comes out to 30,240, and the only unit left is degrees. Across the bottom, we have 1 times 36 times 1, which is just 36. 30,240 divided by 36 is 840 degrees. So in the amount of time that they gave us, the planet rotates 840 degrees. Next problem. A new airplane can travel at speeds up to 4,680 miles per hour. How many miles can the airplane travel in 10 seconds? Here, the starting value is 10 seconds. When we multiply in our conversion factor of 4,680 miles in 1 hour, we should put the hours on the bottom. Although we have 2 different units of time, you should still put them on opposite sides of the fraction. We can make up for the fact that the units of hours and seconds don't match up by throwing in some more conversion factors. There's 1 hour and 60 minutes, and it's purposely arranged to make the hours cancel. And there's 1 minute and 60 seconds, purposely arranged with minutes on the top to make the minutes on the bottom cancel. So, we have hours on the top, hours on the bottom, minutes on the top, minutes on the bottom, and seconds on the top, seconds on the bottom. The only unit left is miles. Multiplying across the numerator, we have 10 times 4680 times 1, which is 46,800. Across the bottom, we have 1 times 60 times 60, which is 3,600. 46,800 divided by 3,600 is 13. So, in 10 seconds, the planet has traveled 13 miles.